and up on the website. So thank you, Peter. Do we have anybody new here? Which Frank is that? Is that our Frank?
There is the only one and only, isn't it?
Well, who knows? Could be. Anyways, okay. So on the agenda tonight, we've got Dave talking about FFT on your scope. Wayne is going to talk about some LT Spice tips and importing models. Kevin's got some cool chip. And Peter's going to talk about his Arduino voltmeter data logger. So, Dave, if you're ready to go, you want to go ahead first?
Yeah, let me see if I can make this thing work. So I got two videos. The first one is 17 minutes long, and the second one 5 minutes long. So the first one is just how to do a FFT on the scope, and the second video is how do you set the appropriate impedance, the load impedance, to make sure you get a correct reading coming out, and it's got a calculation that I do. Let me see, okay. Will this work?
Oh, just a quick interruption. If you guys put up your hand to ask a question or comment, do it a few times so I can catch it. Sometimes it goes up and then comes right down right away. So do it a few times.
Okay, it's telling me waiting for YouTube.
You may have to do it properly. You should do some math calculations.
I can see YouTube.
But I'm not going to do it. I'm just going to give you.
You guys can see it?
Back of an envelope kind of.
I can see a YouTube with a arrow ready to run.
On the signal and scope.
Okay, it's saying waiting.
So I can see it. It's moving. I hear you talking.
My old
How come I can't see it?
It's basically the same way you
Oh, I can see it, Dave.
Well, right here I've got my probe 1 connected to.
Is it working?
Signal generator.
It's fine for me.
I'm just using
I don't see it running.
PARC
That's fine for me.
prototype for the signal generator, and I've got the
I can see
probe
it.
connected.
Oh, there. Okay, now it just came up in my.
Oh, starting to go. There we go.
So in this video, I'll demonstrate how to use the FFT function on the Signalant SD1202 scope, and it's fairly straightforward to do it. You may have to do it properly. You should do some math calculations, but I'm not going to do it. I'm just going to give you kind of a back of an envelope kind of view of it. But the way you set up the FFT on the Signalant scope is exactly the same as you would set up the FFT on the my old Instec scope. It's basically the same way you would set it up. So basically you would go, well, right here I've got my probe 1 connected to the signal generator. I'm just using the PARC prototype for the signal generator, and I've got the probe connected to the output of that clock 0, which is 4.91 megahertz, 4.91 megahertz, so you can see it right there. And that's the signal there. It's a square wave. Got a little bit of ringing due to the probe. Probe's not, I guess, perfectly terminated. And it's adding some inductance and capacitance, so you're getting that ringing. But the way that you would use your FFT is you would hit the math button, and under the math operator here, you can select various things, and you would select FFT. Right now it's already selected as an FFT. The next thing, you have to select a source. So if you were to hit this button, it would select the source. Right now I only have channel 1 enabled, but if I had channel 2 enabled, and let me go back to math, go back here, I could select either channel 1 or channel 2. So I'm just going to go and disable channel 2. We don't need it, just cluttering the screen. So the next thing is the window, and depending what resolution you want, the window is kind of, it's taking off extraneous frequencies. It's kind of taking the signal and it's putting an envelope across the signal. Hanning is the default. If you use Blackman, you get better amplitude resolution, and the other Hamming and rectangular, you get better frequency resolution. So depending what you want, you would pick your window. I just usually leave it at Hanning, but apparently if you select the Blackman, and the way you select this is by moving your universal cursor adjustment knob here. You would turn that, and that allows you to select what you need. So you select Blackman, and then you push the button to select it, and it's selected. The center frequency is, if you look at the center here of the display, that's going to be what the frequency, it's going to shift this FFT, so it's going to be measuring, it's going to place that frequency right at that center mark. The horizontal, the hertz per division, is telling you what the resolution is per division. So right there it's set to 20 megahertz per division. So if we were to go in and use the cursors, push the cursors, and you could select the horizontal cursors or the vertical cursors. This cursor is selecting your time base, and in this case it would be frequency, and in this case it would be amplitude. That measures amplitude, or you could turn them both on. But right now the source is set to math. You could set your cursors to go to channel 1 to measure amplitude like voltage or time. But we've got it selected right now for source. I've got it selected to measure frequency so it's got the vertical cursors, but it's measuring horizontal resolution. I think it's called the horizontal cursors, but I could be wrong. So then you just go and adjust. So let's measure what the actual division here is. So if we come over here, place 1, cursor there, push the button. Now both cursors are highlighted, so if you were to move, you'd move both of them. Push it again, and then the other one's selected, so let's move that to there. And now if you look at the little display here, that's showing you the data from the cursors. So it's showing you the frequency of those cursors, and the delta is showing it's 20 megahertz. So that is in fact correct. If you go back to math, it was showing 20 megahertz per division, so each division is showing you 20 megahertz. If we wanted to go and measure those peaks and look at the frequency between those peaks, you could take the cursor over, put it on one peak, take the other cursor, move it over to another peak. So now the cursors are measuring the frequency. So this first cursor here, that I guess is X2 because that's measuring lower frequency. That's measuring 4.3 megahertz, and the next peak there, it's 14.7 megahertz. Now the problem with this is pretty narrow, and your resolution sucks. It's saying that you're measuring 20 megahertz per division, and that's not very good. So if we were to go ahead and change this, use the cursor here to change this, and let's try and lower it down. You could raise it up, so there's 200 megahertz per division. You can't see anything. So let's go out to 5 megahertz. Oh, yuck, look at that. Look how wide those peaks are, and that's because we're looking at 5 megahertz per division. So if we were to go down to say 48 kilohertz, you can't see anything because the problem is the time base is too quick. It's not capturing enough data to do the FFT. So what we need to do now is we need to go and change our time base. Right now it's set to 200 nanoseconds per division, so we need to go and increase that. So as you increase that, you'll see the resolution here now getting better and better. So if I was to dial this down, let's go to 100 kilohertz. As I change the time base, well, I guess there's no frequency there, but you get to see more resolution. So the way you change your center frequency, so let's change our center frequency to be the 4.9 megahertz of my signal generator. So push that. You could dial it. You could change it by moving the dial. Or if you push the button, a little calculator screen comes up, a little keypad, and you can use the cursor. If you turn the cursor, you can change the numbers there. So let's go on 4, push the button to select 4, move over to point, push the button to, oops, let me clear this. That's a problem with this, it's a pain in the butt to use. So 4, point, 9, and then you've got here, this is milli, killa, mega, giga, and I don't know what the T is. So we just go over to M for mega. So that's 4.9 megahertz, and there's our signal there, our 4.9 megahertz signal. So let's go ahead and change the time base, and you'll see here I'm going to increase the time base. You'll see the peaks getting wider, the resolution's getting worse. So as you change your time base, you get better resolution. So for example there, suppose we wanted to see the harmonics. So 4.9 megahertz, we would want to get another harmonic in here, so we'd want to increase our resolution there, horizontal resolution, to get a 9 megahertz peak. There's a 9 megahertz peak coming in, and the way we could verify that, let's go back to cursor, push the cursor, and let's move one of our cursors over. See, as I'm moving this cursor, the X2 is changing. So I'm over there. See, it's 9.8. So that is a harmonic of that 4.9 megahertz peak there. So let's continue. Go back to math, push the horizontal resolution, and let's change that now. We're at 1 megahertz. So that's 1 megahertz, 2, 3. So that's 4.9, 5.9, 6.9, 7.9, 8.9, 9.9. That's why it's showing up there. So let's change that to 2. Now all of a sudden you see this thing shrinks. And that's because we've got such a large resolution here, and we're not sampling enough to pull that across. So again, you would change your time base. I went and I changed, see, my time base was 200 microseconds there, and I went and I changed my time base to 500 microseconds, okay, per division, and all of a sudden I've got more of the screen filled up. I'm pulling in more data. So let me go up to 1 millisecond. Usually I sample it, I have it going at 1 or 2 milliseconds, and there's the 4.9 megahertz peak. If I go back to cursor, push the cursor button, and I move my cursor over, you'll see that is in fact the, oops, no, it's not, that's 5.7 megahertz, so we need to move that over some more. Oh, I went back to 200 kilohertz. That should be up to 2 megahertz. There we go. I changed it to 1 megahertz, and looks as if I can't get any better resolution than that. So there's the 4.9, the 9.8 megahertz harmonic. But that's generally how you would do it. Now if you wanted to measure the amplitude, the signal strength here, you would go to cursor and you would select the horizontal lines or the vertical measurement. And again, you could move your line. So right there, that's showing me that that signal is at 16 dBm. Now, you've got some options in terms of measuring things here. And let's just go to the next page. And I'll talk about dBm in a second, but how to measure dBm and other values. But let's just talk about some of these other things here. You've got a scale which is telling you the vertical resolution. So the resolution here is 20 dB per division there. So if we were to go and change this, see if I take it to 5, it disappears off the screen because it's too high resolution. Now the reference level, this is what's saying that that's moving your reference level, so it's shifting the display up or down. So if I wanted to get a better resolution, say 10, oops, go to 20, go to 10, see it shifts the whole display down, so I can go over here now and I can shift the display up. Oh, moving it the wrong way. There, I can move it up. See it, but now at that resolution, the noise here looks to be very large. Now, the other option you've got here, this is in split screen mode. It's showing the signal here, and it's showing the FFT here. I like this mode because I can see the signal, but you can go to the next page, and you can go to display, and you can, sorry, not there. Where is it? Oh, here, mode. Split screen, you go to full screen. Or exclusive, sorry. You go to exclusive, then it takes up the whole screen. Right, and let's go back to 20 dB. And let's move this back. Move this back down. So there you got, so you could see a lot more by going to exclusive mode on the display option here. Now this is where you could select your units. Here you can change, you can put what your impedance is. So for example, you could put in here, you push the button, you could say, okay, it's a 1500 ohm load. So now it's going to calculate dBm, it's going to take the voltage, and it's going to assume that that's a termination resistance, and it's going to give you dBm relative to that. So that's kind of cool. An SA doesn't do that because an SA is fixed. It's 50 ohms, but because our scope probe is a high impedance, it's not really loading the signal down, and whatever signal it reads, whatever voltage it reads, it can assume that it's going into a 50 ohm load or a 1500 ohm load, and it can calculate what the dBm is. So in your units, you can again you use the cursor, the universal knob here. I can't remember what it's called. It's called universal select. So there you can select whether it's going to be dB, volts RMS, volts RMS, or dBm. So you've got an option there to select what you would like. So, and that's basically all I have to say about the FFT function. That should give you a general introduction. The best thing is to just go and play around with it and use it, and the more you use it, the better you'll get. And it works pretty good. As I said, I use it to get good ballpark values of frequencies and amplitudes of signals.
Okay, now I got to figure out how to stop this thing. Okay, there we go. So that was the first video. It's just an overview of, just doing the FFT on the scope. I've got another video. It's 5 minutes long, and it's showing you that termination resistance, 1500 ohms, 50 ohms, and showing you that that's actually accurate. I was really surprised when I did the actual calculation based on numbers. It came out bang on, and I was really, really surprised. So I'll go ahead and I'll start that. Let me find the, where is it? Where is it? Here it is here. Okay, and let me get this to show now. Was the quality okay before? Was sound okay? You guys heard it okay?
Yeah, it's fine.
There is an
That's
FFT
reasonable.
function, and I can use that to
Okay,
calculate
what's it doing?
the dBm reading for a signal. And what
No
basically the
audio.
probe is doing,
I have
it's
audio.
measuring a voltage
Yeah, I've got audio.
coming into the scope. Then
It's
it takes
thinking
that
about it.
voltage,
Nothing's come up on my
and
screen yet.
you set the impedance for that.
Don't worry about it,
you're
Dave.
measuring,
It's
and
working.
it takes that voltage, calculates the power into that load, and calculates the dBm. And here I'm going to demonstrate how that works. So right now I've got my channel
just
1 of
lost
my
audio.
scope probe here.
Yeah, same here.
Going to
Yeah, I think it still hasn't spooled up yet. Give it a second.
SIGGEN prototype.
This happened
My
last.
And I'm measuring
My audio is fine.
clock 0, which is set for 4.91 megahertz. And right now that's the signal right there. And I've got my time base set to 10 milliseconds, so you can't really see the waveform. I did that because the FFT needs a lot of data coming in. It needs a
No,
very
I'm not hearing anything.
wide time frame
Yeah, I'm not
to
seeing
sample
anything
the
as
data
well.
to get the appropriate resolution.
Well, it's working fine over here.
Turn on the FFT function here,
Working
and
fine for
automatically
Al.
see a peak. I've already
I'm seeing
got
it here,
set up
Michael, V3TI.
to be
Is everyone seeing it? Because I'm not seeing anything.
4913,
See
Yeah,
it, just
I'm
can't
I'm
hear
seeing
it.
it as well, yeah.
and I'm using
I just have video, no audio.
hertz resolution, black
I have both.
window,
No, the audio's gone.
and the source is
Yeah,
changed.
okay, I'm going to stop it. And I'll just show
And,
it.
there's the peak there.
Here, I'll just start the video on my screen here, and
That's strange that it's inconsistent. It was flawless on my end.
yeah, no,
I agree. It was flawless on my end as well.
is it working now?
Yes.
Because I could see it. I could see it now on my screen. Can everyone see it?
Can't see anything here, just see you and the other guys.
You have to be
Okay.
drinking a stout, and then it's flawless.
Yeah, I'm going to stop this.
Yeah, you know what you need to do? Go to where you see everybody. When you
It's
see
okay now.
everybody, you can select the screen that's showing the video.
Yeah, I'll just, you know what? I'll just do it the old school. You guys could see my screen, right?
Yep.
Yep.
Interestingly, I don't think this has happened before, but your video shows up as another participant square, eh? So that may be why you're not seeing it, Dave. It's showing up as a separate square. You might have to actually select that square to see it on your end.
Yeah, I find this YouTube thing, it doesn't work very well. Okay, anyway, so I'm sharing my screen. I got the video, and I'm going to hit play. It's okay? You guys are seeing it?
Yep. Yep. Good.
Scope, there is an FFT function, and I can use that to calculate the dBm reading for the signal. And what basically the probe is doing, it's measuring a voltage coming into the scope. Then it takes that voltage and you set the impedance for that circuit you're measuring, and it takes that voltage, calculates the power into that load, and calculates the dBm. And And here I'm going to demonstrate how that works. So right now I've got my channel 1 of my scope probe here going to the PARC SIGGEN prototype, and I'm measuring clock 0, which is set for 4.91 megahertz. And right now that's the signal right there. And I've got my time base set to 10 milliseconds, so you can't really see the waveform. I did that because the FFT needs a lot of data coming in. It needs a very wide time frame to sample the data to get the appropriate resolution. So I'm going to go ahead and turn on the FFT function here and automatically see a peak. I've already got it set up to be, the center is 4913 megahertz, and I'm using 100 hertz resolution, Blackman window, and the source is channel 1. And there's the peak there. And if we go to the second menu and we go to the dBm load, the load menu, we go back, see the load menu here. And I've got the units set to dBm, and I've got right now the external load set to 1.5K. So based on 1.5K, my marker here, which is Y2, is showing it 5 dBm. So now I'm going to go and change that.
Can you get it?
And we'll see what happens. So I'm going to take that down to 50 ohms. So there it's at 50 ohms. And let's give it a second for it to convert. And let's now go back to cursors and let's measure what the peak of that is. So now it's saying the peak is 10 plus 10 dBm. So let's go do some math and let's take a look at that. First thing I want to do though, let's find out what the amplitude of this waveform is. So I'm going to go ahead, hit my measure button, my statistics comes up, and if you look at the RMS value, it's roughly about 723, and it looks like it's going up slowly. It's roughly about 723 millivolts RMS. So let's use that and let's calculate what the dBm is going to be into 50 ohms and in 1500. Here's a calculation here, and just one note. I did this prior to filming the video, and I used 724 millivolts RMS, and on the scope we're seeing roughly about 723, but it's close enough, and I think we're gonna get some meaningful values. So basically, the way you calculate dBm, it's the log of two power ratios where you're comparing it to 1 milliwatt. So now the output power versus input power, and the input power is in 1 milliwatt, is V squared over R. And V squared over R has to be in milliwatts. So if we take a look at the 50 ohm load, it's 724 volts squared divided by 50 times 1000, because we want this value in millivolts, divided by milliwatts divided by 1 milliwatt, that comes out to 10.2 dBm. We saw 10 dBm, so that's an agreement there. For 1500 ohms, same calculation except R becomes 1500 ohms, and the ratio comes out to be about 4.6, minus 4.6. We saw just over minus 5 dBm. So you can see the scope is actually using that load, the impedance that you dial in for calculating the dBm. So we could use this function to probe a circuit that's not 50 ohms. It could be any impedance, as long as we know what the source and load impedance is of the circuit. We can use the scope 10x probe to probe the circuit and get us the dBm value. On my signal at 12.
Okay, so that's it. Did you guys see that video okay?
Yeah, good.
So the bottom line is that it doesn't matter what circuit you're probing. It could be any impedance you want, as long as it's under 1500 ohms. You just dial in the impedance in the scope, and the scope does the calculation based on that impedance. That's not a termination impedance, that's just a calculation impedance. So you get an accurate dBm reading. So that's pretty cool. A spectrum analyzer does not do that. It's only at 50 ohms. So if you use a spectrum analyzer to probe, like say a crystal filter, which might be say 400 ohms or 600 ohms, use a spectrum analyzer, that 50 ohms is going to load the crystal, and it's going to, the peaks are going to broaden out. You won't get accurate data. You could use your scope probe at 10x and dial in 600 ohms, and you're going to see the proper frequency there. So that's pretty cool. So yeah, Peter.
Dave, I know you got the spectrum analyzer, and you were forced to use your scope as a spectrum analyzer due to the project that was going on at the time. So you've had a pretty good handle on using the FFT function on your scope, and of course the SA. How did you find using the scope on I guess it was the D612 project, and going through all that stuff? I know it would have been easier with the SA, but how did you find using the scope's FFT function?
It was fine. It just, you hit the nail on the head. It's just much more work, because you got to be going and dialing in and changing buttons, and the SA, you just hit one button and it does it for you, right? So yeah, it's more work, but I got values. The key thing was just the delta values I was looking at, and that was bang on. I think, who else? I think Michael. Who else had the, yeah, Michael?
Yeah, Dave, I have the same scope as you now, anyway. When I just tried, just before the meeting, I tried looking at a 7 megahertz signal out of the signal generator. I had thought that the signal generator puts it a square wave, right?
Yeah, that's right.
So I would have thought I would have thought that when you look at the spectrum on a square wave, don't you get the first, third, and fifth harmonics out of it?
Yeah, you get the odd harmonics. That's right.
But you're seeing, but I'm not seeing that. I'm seeing 7. I'm seeing 14, just like you saw, 4.9 something and 9. That's not three times.
Perfect. Yeah, I don't think it's a perfect square wave, because you got the ringing.
Yeah.
You got other stuff coming in, so I don't think it's perfect, right? And so and there's always going to be some kind of artifacts. You can't get a perfect square wave, right?
Okay. So the other thing is, I tried, the first thing I tried was you just using the scope probes, which gives you the ringing and overshoot and stuff. So then I thought, well, okay, I'll use just a 50 ohm BNC to BNC cable and connect it directly to the signal generator and put a 50 ohm termination at the scope terminal. So that means it's the signal generator is 50 ohms out. So the scope at the scope input is also 50 ohms. So is that the right way to do it?
Yeah,
and I set my times to 1 times.
Yeah, if you can, like in my video, I didn't say it, but the spectrum analyzer was terminated to a 50 ohm resistor, it was terminated at 50 ohms. If you're going to take the signal generator and feed it directly into your scope, then yes, you would connect a BNC cable, put a T connector and a 50 ohm terminator at the other end, because that signal has got to be terminated at 50 ohms, because the scope is like what, 1 meg?
Yeah.
Yeah, so you have to terminate that signal, right? Same thing, if you're using the probe, it's not a problem using the probe, but you just got to make sure you go in the FFT function and you tell it that it's a scope probe and the scope probe is measuring a 50 ohm circuit. Otherwise, if you have it, you know, coax going to a T connector and a 50 ohm load, you have to go and tell the scope again, it's a 50 ohm termination. You have to make sure you do that. If you don't do that, all your readings are going to be incorrect.
So you can use the regular scope probes then, but you would terminate them at the scope and a 50 ohm load, right? With your T.
If you're using the scope probe, you don't have to you have to terminate the signal. You have to make sure the signal's terminated and you're probing the circuit, right? But if you're going to feed your signal directly into the scope, then you use a T connector and you terminate it, right?
EMRFD book has a good 2 pages of 2 ways of measuring with a probe and without a probe.
So you see, you would take your T connector, have a 50 ohm terminator, plug it in, connect that to the scope, and connect your signal source into that. And this now is terminating your signal at 50 ohms. And this T here is now the probe. That's probing the circuit, right?
Yeah. Okay.
But you have to use a 50 ohms cable. Your scope probes may not be 50 ohms, right?
Yes, yes, yes.
Well, that's right. That's why I'm using a piece of 50 ohm cable directly from the signal generator into a 50 ohm terminator at the scope.
Here's my scope probe. So what you wouldn't do, you wouldn't do this. If you do this, that's a big no-no. That's a big no-no, because you've got a high impedance to a low impedance. You've got a voltage divider. You won't see any signal. So this is a big no-no. What Hassan's saying is if you got a 50 ohm cable, as long as you've got a 50 ohm cable, you plug it into your T, and this cable's 50 ohms, you now connect that to your signal, and you're good to go. Right?
Yeah. So if you do it that way, the signal generator is 50 ohm output connected to your 50 ohm cable, and at the other end of the cable, you've got a 50 ohm load connected directly at the scope. Okay. So you shouldn't be using the scope probes to do it then.
Oh, you can, but you're just going to have to terminate. You take the output from your signal, from your SIGGEN. Here's my SIGGEN here.
Mm-hmm.
So you take the output from here, and this is going to go to a 50 ohm terminator. Then you use the probe
right there. Yeah.
to probe that, and that's perfectly fine. You just get a little bit of ringing and stuff, you know. There was a few other people had their hands up.
Yeah, Cherry's next.
Okay.
Go ahead, Cherry.
So what is the model number of that Strickland scope you are showing up there?
Oh, it's the 1202XE.
Okay, thank you.
SDS 1202XE. Like I've got a cheap Instec digital scope here. It's got the FFT. It's not very good, but for doing ratios between measuring 2 peaks, the difference between 2 peaks is pretty good.
Yeah, it's probably good enough too to check harmonics.
Yeah. Oh yeah. Yeah.
So you shouldn't expect to see the first and third harmonic then, given the ringing in the signal?
Yeah, if I connect the SIGGEN and I connect it directly to my SA, I will see the first and third, and there'll be a little tiny little the second harmonic and fourth. You'll see little tiny little blips.
Because I'm seeing quite a bit. I'm seeing double the frequency, quite a strong signal. That's the first thing I see is quite a strong signal at 2 times. Okay.
Yeah, so it's probably ringing. Maybe you don't have it connected up properly. There could be a lot of things.
Okay.
Or actually, Michael, check if the square wave is symmetric.
I was going to say, check your duty cycle.
Duty cycle on what?
On the square wave. If it's off, if it's not exactly 50%, you'll get second harmonics.
And where do I check that? Where do I check that with
You
these?
just have to measure it very accurately.
Okay.
Okay, I think Hassan was next.
My question actually got answered. I was just wondering if Dave had a signal generator in his scope, but it turns out you were using the PARC SIGGEN. So.
No, I've got a no, I don't have the scope has a wonky compensation, like I think it's a 1 or 2 kilohertz a hook where you calibrate the rising and falling edge. But since then, I've got a proper signal generator. I bought one at Dayton, and I don't want to plug it. I'll just show you a picture. That's the proper signal generator I got there, and that generates a true sine wave. You put that in a sine wave, and you only see one peak. And you put in a square wave, and you're going to see only the odds. It's really good.
What's the model number of that, Dave?
It is the SDG 2000X.
Okay.
You see it there?
Yeah, okay, SDG 2000X. Okay, thanks.
Yeah, I can't remember how much I paid for it, but you know what? Hey, man, I tell you, the better equipment you have, the better measurements you're going to make. Because prior to that, I was using, don't laugh, I was using this as my signal generator. I was using this for a long time, and this is not accurate. It is not accurate because I kept looking at going, okay, 0 dBm. 0 dBm is supposed to be blah, 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 peak to peak, and it's not. So it's just for using your S meter. And your S meter is probably, I don't know what the accuracy of that is.
What's the frequency of your SIGGEN?
Sorry?
What frequency does your SIGGEN go to?
Oh, it's 200 meg. Wow, it's 200 meg. Yeah, I purposely got the 200 meg because I do a lot of digital stuff, and I want to see square waves. Because when I go to a 30 megahertz square wave, I don't want to see a sine wave on my scope. I want to see a square wave, or it's squarish.
I have a field tech.
Squarish.
Okay, I have a field tech signal generator. It goes up to 24 megahertz, so it's probably good enough for me, but that I think produces reasonable sine waves. It looks like it anyway on the scope.
So why don't you compare if you compare that to the SIGGEN, then that'll tell you something about the SIGGEN, right?
Yeah, I'm going to. Good idea.
Are you done, Hassan?
Yeah, I'm done. Thanks.
Okay. I think Kevin was up next.
Actually, that's okay. It got answered too. So
okay.
Go ahead. Next.
I don't see any more hands up.
Any more questions, comments?
The other thing what you could do, Ken, is if you take your mouse, I just noticed this, and you hover across everyone's little thumbnail, you could see if who's got their hands up.
Yeah, I noticed that before, but it doesn't always work.
Yeah. Okay.
One last question. I forgot. Oh yes, those videos are on YouTube, aren't they?
Yeah.
On your YouTube channel.
Yep.
Okay. Thanks.
There's actually I found I loaded a couple of videos there on my transistor tracer too. I'd forgotten I did that.
Okay, cool.
Okay, I'll shut up now.
I'll stop asking questions.
Alrighty, so if we're done, Wayne is up next. Take it away, Wayne.
Okay, first, you guys can hear me?
Yep, no problem.
Yep.
It's not always the case, just had to check. All right, so, whoops, that's the wrong way to think. First, I have to figure out how to share my screen. Oh, here it is. Duh. Okay, go down. Entire screen share. Close you and okay, you should be looking now at my AltSpice screen. Everybody okay?
Not yet. Nope,
Okay,
it's
seeing a
blank screen.
Okay, cool.
I see your mouse.
Isn't that interesting? What should I do about that?
Do you have multiple screens?
I have multiple screens.
Yeah, so you selected the wrong screen.
Oh, I'm sorry. No, I don't have multiple monitors. I have. That is not.
Did you select an application or select the screen? Just select the entire screen.
I selected the entire screen. Yeah.
Oh, really?
I think you need to select the application, though.
No, you can do the entire screen. I mean, I did that last time, basically, with my PowerPoint presentation.
Stop and start it again.
Stop and start the application, not the session, right? Just check it. Okay.
Oh, the sharing. Stop the sharing and try that, and starting it again.
Stopping the sharing because you. Okay. Don't want to raise my hand. I do want to share my screen. There it is. My entire screen. Please share. And I'm looking at you guys.
I still say you have to go to the application.
Okay, don't mind doing that, but I had to bring the application up now.
Just make sure your application window's open, or I mean the window's open of the application you want to share.
Okay, coming up. All right, so stopping the sharing, starting the sharing one more time. This time, I want an application window, thank you. Geez, I got a lot open.
Yeah, actually, I've been having problem with Jitsi all week. I had a session the other day, and one guy just kept dropping. He'd be on for 5 minutes, and he'd just drop. And like YouTube today wouldn't work very well. So I think Jitsi's not behaving well.
Well, here's a good story. I have opened my LT-Spice, which is my entire presentation. When I'm trying to share my screen, I don't see it on my application windows. It's not there.
You have is the window closed for LT-Spice or is it open?
It's open.
Okay, I was gonna say make sure it's open and then just tab into the into Jitsi and then share application.
Okay, I got what you're saying. So I'm here now. I have to unshare again. Cancel. I haven't actually shared yet, have I? Okay, here I go. Tabbing into the presentation. Look for the application. There it is. Okay. Okay, so it's telling me that it's sharing my Jitsi.
Yeah, for some reason it's not going into your application window.
Oh, this bites. Okay.
Why don't you try closing your browser, reopening it again, and coming back into Jitsi? Just restart everything.
I'm going to do that now. Just hang on a sec. It'll take a few secs. Signing off now.
Yeah, like I said, this week, this is the second time where I've been having problems with Jitsi. I don't know what's going on.
I wonder if we can convince the club to buy a Zoom account.
Yeah. Seems everybody now is using Zoom.
Yeah. It's probably only a couple $100 a year. I can't remember how much it is.
I think it's $20 a month. I think that Mississauga Club's got one. I think it's $20 a month.
So it's a couple $100 a year, like
Yeah.
$250 or something like that a year.
Is it unlimited?
I think so, yeah.
Well, I think they're unlimited to like 150 participants or something.
Okay, but what happens? What happens if the Aries wants to use Zoom and we want to use Zoom on the same night?
I don't know whether you can do that. I know
no problem. Just schedule it.
Yeah. Okay.
I use it for the bureau, and the club uses it for stuff too. So it works as long as you keep the times separate, I guess.
Yeah, okay. Because I know that some of the other club meetings are happening on one of our 2 nights.
Oh.
I use Teams now at work, and I tell you, I remember Joe. Remember Kevin, Peter, way back. Joe was telling us, "Oh, we should use Teams.
Yeah.
Teams is the way to go." He's right. He's 100% right.
Yeah, that's what we use at work too.
But it costs money, right?
I'm not paying for it.
Yeah, but your work is. You got to have Office 365, right, or something.
Yeah, that's his problem. He wants to use it. He's got to pay for it.
Yeah.
Okay, so I'm back. Can you hear me again?
Yep.
I can hear you, Wayne.
So usually the problem is you can't hear anything I'm saying. So let me just try opening that guy up again.
The key is to make sure that your LT Spice application window is open, not minimized.
So it's maximized.
Yeah.
Well, if it's maximized as it is, then I toggle across to the
Jitsi.
Jitsi.
Yeah, and then when you go into the share screen, in that screen you'll see where it's there, share your entire screen or application window. If you click on application window, you should see your LT Spice window.
Oh, I do.
Now click onto that. There you go.
There we go.
There you go. Good.
Excellent.
That's it. Yeah.
Okay. Now I forgot what I was going to say. All right. So what I'm doing here is I'm going to tell you about stuff that I've already heard presented here. It's just that I couldn't learn it at the time. So I thought to myself, the one way to prove that I think I know it is to try it out on you guys. Second is you may have the same kind of problems I was having understanding what's going on. So what I'm going to talk about is how to import models that are third-party models, or maybe your own third-party models into LT Spice, and I'm going to take it through kind of like how I beat it to my head. So one of the things that I have problems with is really I don't understand when I build a circuit, like using an inductor that I got the cursor on, what's actually going on under the covers. Like, how does it know it's an inductor? If it's an inductor, how does it know what the value is? How does it connect it? Things like that. Now, components are pretty simple, but when you get up to these bigger, ICs and stuff like that, with many pins on them, confuses me how it knows where the voltages are and stuff like that. So, what I'm going to do is try to take you through a series of files. Now, this is going to be a problem because I want to share my entire screen. So I'm going to try that next, okay? Because I got to open up a file in a text editor in a moment. First, I'll just show you the stuff that I'm not going to talk about. The passive stuff is basically files that you cannot edit or see, really. You just use the application to see them. You're actually able to, I didn't realize this for a long time, is you can select an inductor off of a list if you choose to. And if you want to quit an edit database, you go into a freeform edit. So you can actually add your own inductors to the list inside the application, because that's got to be the most useful thing you would ever done. But that's a feature that is true of the capacitors and inductors, the ferrites, the crystals crystals and ferrite beads are inductors and capacitors just under the covers. They just have a different front end. They're making use of the parasitics and resistors. For the passives, The whole purpose of this stuff is to allow you to select a value from a list that you basically have to maintain, because they provide you with things like 5, 10, 15 picofarads and stuff like that. When you move to the semiconductor models, those models have, how should I say, LT Spice understands how to work with semiconductor to be fed some parameters. So were I to look at a diode, it has a SPICE model. Well, the SPICE model is on a diode because it's a model of a component. The model is D. Everything in the parentheses are just basically some parameters that are fed into it to feed the internal model of the software. So it knows what a diode looks like. It knows certain things. It might need to know the voltage ratings. It might need to know certain characteristics of the shape of the curve and that sort of stuff, and it takes care of the rest for you. Now, if you want to look at a diode, actually, I should tell you about this because my list is probably different than your list. There's a guy named Bordanov. He's available off of the LT Spice wiki. He's collected massive amounts of information about various different types of components. And if you choose to, as I have, you can sort of download his formulaic lists of components. As I found it, it has more components in it that are of interest to me than the actual out-of-the-box LT Spice list. However, it's burdened with a lot of these Russian guys, okay? The Russian guys, you're not going to find here in North America, so they're at the top unless you sort it. Now, what I want to do before I carry on is I'm going to try to see if I can share my screen, since sharing seems to work now. It'll be better for the presentation if I can show you what I'm doing in the files. All right, so here I go again. I'm going to share one more time and hope for the best. This is my entire screen. Okay, are you seeing? Can you see anything at all?
Yep.
Yeah.
Oh God, that's good. Okay.
Okay, so before.
Now we can have fun. All right, so what I'm going to do now is go into the actual libraries a little bit. On your machine, under LT Spice, wherever it's held. In my case, I found that my LT Spice information is actually in my documents. Most people will probably have it in the program files folder, which is properly where it goes, but somehow I managed to sneak this one past the installer, and it's very convenient for me because it's easier basically to do maintenance this way. Components are held in the component subdirectory of library. The code, where you have subcircuits and libraries, is out of the box in the sub directory. And the pictures, the things that I'm actually interested in trying to figure out things to connect together, is in the symbols file. If I wanted to add a standard value or a new value for a diode, well, let me take a binary, a normal transistor here, because I've set it up. If you look at it, you can open it up with Notepad or even Word, and it comes up as text, which means actually, if you want to, you can go online, which I'm going to try to do in front of you, okay? And you can dial in one of the various places that have models and find yourself a diode model and just poke it in. Here's a diode model. All right, there's a diode model. Don't know what it does. Love it to pieces, so I'm going to take it. So I'm just going to take that, Control C. I go to the top here. I left the period out, so I should put that back in. And that's my model. I can tidy it up. Don't have to. So all I did was remove the plus signs, and hopefully that'll work. And then what you do is you save it. I'm scared to death of doing this because it might fail, but I'll do it anyways. And when you save it, you will not see it. Oops, gotta stop doing that. For some reason, I want to go into KiCad all the time. All right, you'll not see it on this list yet. Actually, you will. No, you won't. What you have to do first is leave the, you have to leave LT Spice and come back in. And because what it's doing is it's loading this entire list on startup. There we go. Going to bring this back up. Oops, that's the wrong file. Try that again. And if you right click on this, the normal thing you do is pick a new diode. Do I see it? Not yet. Is there a reason? It's because I was doing an NPN transistor. I'm an idiot. Try that one again. Gosh, this is complicated. It's because I think it's a good idea to put every single thing I use in the bottom bar. It's not. Actually, it's burden finding stuff. Try that one again, NPN. Go away. Let's see, pick new transistor. And I still don't think I'm seeing it, am I?
I thought you picked it as a diode.
Did I pick a diode?
No, but he put it in his model is ZC830A. It should show up as a transistor. Just do sort based on part number.
Let me do one thing first. Okay, yeah, it's saved. I've done this already once, so I sorted on part number. I'll troll to the bottom. Z to something. No, it's not there. Works when you do it right. Can't explain that one. I'm not going to spend too much time on it because this does in fact work when you do it. CMP, BJT file, open it. Yep, it's there. Z83A.
But it's a D. Change maybe, why don't you try changing that D right beside it to an NPN?
Oh, that's what you're trying to tell me.
Yeah.
I did pull up a diode. That's a bad thing.
Yeah, so.
Let me just put it in diode file, okay?
Or you could just copy and paste an existing model and just rename it, right?
I was just about to do that, actually. Because I think one of the values of this technique, a lot of people may not want to actually mess with the actual files. They may want to use another method. I don't have that problem. I'm brainless, so it doesn't really bother me. But what you might want to do is actually reorder the list so that the parts that you use most often actually are automatically on the top of the file. And you do that by just cutting and pasting them. Let's try this one again. There it is. Okay, so it put it in the top of the file where it was. And I won't, because I lost a little talking time here. I won't go into any files and move things around, but you know, I've got a parts bin and like everybody else, a big bunch of spare parts. But you know, 90% of what I use is for transistors. This is 2N3904. For diodes, it's the 1N4148 for the signal stuff, and I use a 1N4001. Even if I sort it in order, I've got to scroll down to find it. So it might not hurt to have it at the top for speed. But basically, that's it. You've added a model and you're on your business, okay? So you can use the technique of opening the file and editing it, if you choose to, on any of the files that are in the directory called CMP, and it works like gangbusters, providing you stick diodes in the diode file and not in the transistor file, okay? So there are files for the FETs, MOSFETs, JFETs, MOSFETs. You've got the inductors, the capacitors. Again, ferrites are in the inductors file. There are no crystals in the crystal file, but they're modeled that way. And if you wanted to use the editor, you could add your own crystals there. Okay. So that was the first one. That's the easiest way I can think of doing it. We're going to move up the ladder just a little bit to the part where it gets sort of weird for me. Not too weird. This is pretty simple. Okay, so the next way you might want to add a component is actually to drop the text into your diagram. So this is a way that's construed to be very portable. You can drop the model into your diagram, and as we'll see, you can drop a reference to a file stored on your hard drive into your, and you can even drop a link to a URL where the model actually sits if you choose to. And if you
Oh, we lost him.
find that model, so it's a good thing. I don't have that problem, so I'm sharing my models. One thing you probably want to remember to do when you bring in a model is you should test it when you bring it in, all right? So I set these things up so that I have a very simple, I'm really testing the transistor's frequency response, say, in this stupid circuit. I don't know anything about it, but I can test the voltage in the diode and make sure it's, looking right. All right, so thing, and I were to type the voltage on there. Yeah, that looks about right. At the lowest level, it comes up through the capacitors are basically open circuits at the low end, and it brings itself up. So what it means is I do have, in fact, a transistor model. Okay, that's basically what it is. When they're talking about you should test the model, most people are talking, I think, about the high-end stuff, like making sure that the parasitics baked in the model are performing as you expect in your model, or you might not get what you're really expecting to get out of it. But it's very simple to do. So this technique, of course, works for the higher end models, which are actually subcircuits. And I will just bring up, that one's actually later. Op-amp models. I'm going to open this up. Pretty much the same thing. Now here's kind of the reason why perhaps sharing it as text inside your diagram is not going to work for long. I only got 2 of them in here, and it's using up all the space, and you can't actually see anything unless you ramp it up. So the technique for op-amps is what LT Spice has done, and maybe this is just like normal for all vendors, is they've actually developed a special operational amplifier that's designed for usability with third-party models. Okay, I want to bring this one first because it shows the actual models on the screen, and all operational models, if they're built using the convention that seems to be around, are built the same way. They're built so that the parameters, which are on this line here, subcircuit NE5532 1, 2, 3, 4, 5. It has 5 parameters, and the parameters are the inverting input. I'm sorry, the non-inverting, the inverting, the positive, and the negative supply, and the output. Basically, I have not been able to find anybody who's not following the convention, but you may run across one, and if you do, you got to be careful because it's expected by LT Spice that you are. You get into some trouble modifying the file. Maybe it's not trouble, but you have to modify the file that's actually driving this. So I'm going to look at those files in a moment. When I bring in a symbol, I'm just going to actually change out this symbol. I got to move my camera because it's in front of the components bar. The special thing is op-amp 2. There's an op-amp 1 as well. That's op-amp. This is op-amp 2. Op-amp 2 has 5 components to it. Whoops. Stop that. Nope. Did it again. I'm going to kill myself, man. Stop that. All right. Op-amp 2 again, and here I am again, has the 5 inputs. It has the 5 connections that you need here. What you do when you use it is, let me drag this out of the way, is you put it into circuit. Get rid of you so you don't break my thing. And you go into it like so, and you text edit that op-amp 2 to a name. The name must match, in this case, because I've had them on screen, must be the same. I'm going to 5533. That says NE 5532. If I run my simulation, let me think for a minute. Just got to make sure I did what I thought I did. No, I have them in comments first because I wanted to turn them on.
Should be 32.
Yeah, it should be 32 because it's 33. It'll fail. But since I already showed you that, I will put them both in spice directives and run it. Okay, so I did something funny here. Oh yeah, I forgot. I don't know what I did there, but I don't care. Oh yes, I know what I did. It was working, but if you look at this thing here, it's got a really strange name to it. Maybe I can fix it. The reason it failed on the actual op amp is if you look at the name in here. Look at that. It's 741-NS. I just don't like that, so I changed it in my earlier stuff. NE 5741 741/NS is what I see on the screen. Just
it's LM. It's LM.
It is. Thank you, sir. I would have just demonstrated how it doesn't work when you do it wrong, but I've already done that, so all good. Now, going to put up these models here. I'll add a plot pane for them. This is the 5532, and here's the LM. Sorry, let me do that again. Click. You can maybe a little hard to see, but the green line, which is the higher performance one, extends farther right in the frequency domain. That's demonstrating that you've got the gain bandwidth product is higher in the 5532 than the 341, and that's basically as far as I can do it. You can see, I just wanted to comment on this here. If you look at the model, I'm not even going to say look at the model, just look at the size of the 741 is on the right-hand side and the 5532 is on the left-hand side. What I'm suspecting from this is that somebody's taken a lot more care to take care of minor parasitic type behavior of the 741 that they had to describe in a longer text stream than whoever did the 5532. But that's speculation. But bottom line is, if you look at the two curves, you can see this thing sort of jumps up a little bit higher. I think I actually can't show you that because I've been messing with the frequency domain, but this guy doesn't hop up; he just goes flat. All right, so. Recap. You can include the text for models, and you can include the text for the other arbitrary device that you can find online. Okay, I picked these off of websites. I'm sorry I won't bother wasting your time looking for them. I'm going to go to the next one, which is going to move to using a live file. And which one's a live file? Okay. In this one, now I have to actually show you some stuff. Yeah, so this is... Let me go and take my life in my hands and just bring in something here. No, I think I'll move to a subtopic first because you need to understand how this stuff works. I'm going to go to the symbol files first, and I just want to have a quick look at an actual symbol file. I spent most of my time trying to understand stuff by digging into them. I put up one called testing inside the symbol directory, and we'll be going there in a moment to add one. Let's have a look at something that's out of the box. This op07 is actually a linear tech model, which you can open with Notepad. And this is used to sketch the actual op amp on the screen. So you don't need to know this stuff. No, I don't care. Stuff at the top is basically how it draws right up to here, is the picture. Some of the parts in here relates to things that we're interested in, and this is kind of an important thing that I alluded to before. This is the actual order of the pins. The spice order 1, 2, 3, 4 is how the picture is being connected to the actual spice model. If you don't follow the spice order, if you in fact had in negative where in positive is, your model won't work. But it will be an acceptable model as long as it says 1, 2, 3, 4, 5. Right? It's going to know. LT Spice will assume that the pins are in the right order, so everything's good. So what that means is people are kind of cautious about messing with this file. But I wanted to show you a couple of things about it that are reasonably safe. One is there's a couple of value fields here, and then there's a model field. Okay, you see the model field here. What's going on is LT Spice is putting a whole bunch of models into its internal library called LTClib. This is one of them. I don't think I can open that one because most of the LT libraries are actually encrypted or something. They're just not visible. But knowing that, it allows you to have an option of using a symbol that's already defined in the library and putting it on the page if you want to. Okay, so if you want to make your own live file, or sorry, if you want to use your own live file, you have to have some way to access it. So I have a 741 hiding over here, and I have the, which I'll make big enough for everybody to see. Excuse me, drag it down here. I created a 741 subroutine by taking this text and putting it into a file. What you can tell from looking at my file is I actually put it into the subroutine folder. Now, if you want to store a file in an arbitrary location on your, or maybe even on your hard drive, you must put the entire path in the library statement if it's on the diagram. So what I've done is I put a subroutine file here that replaces the text that's now comments. Okay. Now the subroutine, in my case, is somewhere in here. 741 is hiding in here. I won't waste your time looking for it. The picture that I'm using, I've actually, nope, not subroutines. I put in the symbol files, and I put it in the testing files. So I went here. Oops, let's not do that. You do that from the operating system. It just brings up the editor. I went here like this. It's naturally an op amps, so I went up one. I went to the place where I keep all my testing files, and I'm showing this because if you want to create your own, directory in the symbol file for your own symbols, you can. All right, and then I added this one. Now, when I added this one, I'm not even at it because I'm showing it to you later. It basically produced this. So when I run it, again, well, maybe I should have done that differently. And that one, go here and delete that one. I'm looking at the same picture is what I'm trying to say. So either way works. I'm using a file with a library command, or as earlier, I have the copy in here. So all I'm showing you here is this one is still out of the file. Sorry, this one's still out of the screen. This one's no longer the screen, but it's coming from a file. Okay. Now, many people actually serve up subcircuits in collections called libraries. So you can use library files as well. And in fact, I showed you, that there was in fact a case where LT Spice is actually pointing an op-amp symbol towards a library, which is kind of cool. So if LT Spice can do it, that means we can do it, basically. All right, so I'm going to show you an example where I have done that. First, I want to close this thing. So, no, thank you. All right, so open, please. No, I think I'll do this one first. I'll do the create a symbol first. I've done this once. This is the obvious way to do it. You don't need to do this with operational amplifiers, but there's a way of an approach to creating your own symbol. You would create your own symbol when you have a model for something that is, got 50 pins on it. You need to have a picture of it, and you don't want to try to draw the symbol and mess up the order of the pins, right? So that's how it normally works. So how I created this thing, I'll show you. What you do, and I needed to show this, is you have a library that's visible to you. When I open it up with right-clicking, I see an extra button here. It says open. So it's a live command, and that is where all the, sorry, I didn't show you the live command array. It's just a set of sub circuits, okay? You can use a live command or an include command, which is .inc. I recommend you stick with the live command if you're just putting models in. What the .include function does is it actually reads in things like your simulation commands and op commands and stuff like that. It'll read them all in, and it will actually, if it's there, I mean, it's not always in the files, but it will impact you if you're trying to use it. So the live command here, if you have a library on your directory and you open it, you can see a text file, which is like, I didn't quite understand why you'd want to do this, but it's because what you do is, I think you select this, is that right? Yes. You put your cursor on one of the subcircuits that you're interested in, and you press create symbol, and it automatically creates a symbol for you. Now, it's don't need this again for an operational amplifier, but you got one of those 50 pin suckers that you found off the latest thing that onsemi's made. You really want a little help, right? So what it does is say, are you sure you want to create it? You say yes. It pops you into the screen here, which is actually what is created. You see 1, 2, 3, 4, 5. That was the operands in the actual file itself. So doesn't really matter that it's 1, 2, 3, or 5. You are allowed to actually change the label if you choose to. Like 1 was, what was 1? Plus, and 2 was minus, and plus voltage, 3 voltage, that's right. But I'm not going to do it this time. What you need to know now is where did it go when you created it? It's actually already saved. You didn't have to save it. So when you do create your symbols, they are actually stored in a subdirectory called auto-generated. There it is. There it is right there. Okay. Another thing about it, in that directory, excuse me, auto-generated, is if I've opened this with a text editor, I can see that it's using a different thing. It's using a different term called model file. I forget what it was in the earlier one. I think it was something like sim model or something like that for the LT Spice one. This is actually interesting in how it works, but it basically put the full directory and it points automatically to it. So as long as you don't move this particular file wherever I got it from, it's not going to move again. Okay. Pin names are here. You can change them again in this with the text editor if you choose to. So the main feature is it's putting a value in for you that is the same as you see on the screen. So it's like naming the operational amplifier, and it locates the file for you. So you can get kind of comfortable with how LT Spice does it and essentially directly edit the 2 or 3 lines that matter in the LT Spice rather safely, I think. typically you want to stay away from the spice order, okay? And so what that's all about is you can get a device. If you look at it, that's an NE5532 that is inside a model that basically has the name on it. So I can now you can what I'm trying to say here. You don't have to use op-amp2 anymore because I've actually named it. That's what I'm saying. Is I've created a symbol for one single op-amp that actually connects to an entire library. And since it's doing that, I think I still have to have the library in this case, but I think I have a case where I don't have to have it. I'm not sure. Dave will know. Just remember this, Dave. I'm going to go to my next one now, which is, oops, open. Which is my roll your own. Yeah, here's one where I did it basically by hand. So this is a file I created without recourse to using a library command. What I did is I went to the directory called let's see, it's symbols training here. Symbols testing. And I started with the op-amp 07. It's here now because I put a copy of it here. I duped it. What I did is I first created a copy of the file, and then I updated it and I saved it. So I don't remember what order I did it in. Let me think here. So have a look at this thing. Open with. Okay, it's called Spice Model. There's a difference between Spice Model and Model File, and I'll just explain it rather than bother showing it to you. What I can do is just add this model, and I will put it here. Well, I've got it there. If I right-click on this thing, it says, hey, it's a precision operational amplifier. You cannot edit it, which is, I presume, how Linear Tech is protecting an asset on their drive. They just don't want you to mess with that, okay? And that is caused by one or two different things. It doesn't seem to be caused by the description. It's caused because they're using Spice Model as their operand. However, were you to A, find the file, and B, open the file, take the same file and open it. Here's what I've done. That Russian guy, he has an operational amplifier library. I have put it into my subroutine file folder so I don't have to trouble myself with a very long directory sequence of filing it somewhere else. It's called op-amps AD for analog devices. There's several of them for different vendors, okay? That's my model file. So I changed the syntax, or I changed the, can I put these up at the same time? I don't think so. I have to show them sequencing. I changed that to model file. I changed the name of that. I went into here and I changed that to the name of the op-amp that I wanted. I changed that to the op-amp that I wanted just in case it mattered. And I updated the description. So if you look here, everything else is the same, trust me. But I just changed the file layout so point at the right thing. This is an actual instance of a model in that file, which I suppose I could bring up, but maybe I won't unless you ask me to. And, well, does it run? So I don't know if this thing will work. Oh yeah, I've turned off the thing here. I've got the NE555 still 5532 still here. It's using this guy, and I've got this new guy in here. And what I will do is run my simulation. It's the same simulation every time. I will add a trace. No, let me split the plot planes. The 5532 that's made up of a new symbol seems to run. I'm sorry, that's not the new symbol. That was this one. Try this one. Come on. Are you working? Okay. Oh, I know what I did. There we go. And then I will, that says out 2. I'm going to delete that. Just clicking the wrong thing because I'm all very nervous and stuff. Delete, go away. You too, don't like you, whatever you are. Delete this trace. Out there. Out there. I think you get the picture, but it's not liking me. There we go. And okay, so oh, no wonder it's not working. You guys can tell me how it's not working. I'm using the wrong file because I cleverly forgot to save it. Shall we do this one?
Sure.
Thanks for calling that out. You're nice. Way too nice. Okay, here we go. All right. So you can see this one's different than the other ones because of that blip, which, you know, there's a question of, if I didn't have all this stuff in here, you know, am I actually looking at the thing I'm thinking I'm looking at? If I didn't have in this file a legitimate operational amplifier, it's going to give me an error message, okay? And I can go in and I can edit it. I think this might be one, it might not be. Let's try it, shall we? Is it? No, it's not. So that's the message you get when you've picked the wrong file from something, or if in fact this almost invisible symbol here, if it's ever not pointing to something in the directory, you're going to get shall we see it? That message. Okay. Now, if I were to go into the file, I want to go into my actual folder for it, and scroll down here. That's a little slow. Here's the directory, the library file, I should say. Can open that. I picked the first one, I think. Maybe it was 745. 645 is legitimate. I could use that if I wanted to. But the important thing about this for me is I've got kind of Nirvana. I don't have anything in my file, in my scheme of in my diagram, but the diagram. It's not actually necessary to use a library command on screen if you can mess around with the underlying covers. Now, I'm not here to argue that this is a wise idea, by the way. I mean, you know, if you put a library file like a .live file on your screen, people are going to know you got a library file and they know what it's called and they can look for it and that sort of stuff. It's just, it's part of how I'm trying to figure out how this symbol actually gets executed in code. Okay. And there's a different model. You can see it changed its shape. All right. Because that was me touring through it. I'm basically done now. I'm going to switch over my screens to see if anybody actually did raise their hand, or if you left the meeting. Here we are. Stop sharing.
Oh, we're still here. That was very good. I was lost at some point. Some points.
I apologize. Anything I can talk to? I went pretty quick because I was super nervous, but it also took a long time anyways.
Yeah, I think the point is that, you know, we got to play with it and learn how to use it. Dave, go ahead.
Yeah, I think Peter had his hand up first, but that's okay. I'll beat him to the punch. Yeah, Wayne, it's kind of interesting how you did the include to put the model in the include, because that solves the problem. And I don't know if you realize this, but portability. Because a lot of times I'll do a circuit it'll refer to a model I've got, which I loaded, and I'll send it to Peter or someone. They'll try and load it, and it breaks. Whereas if you've got the model included as an include statement, you could take that file now and you could give it to whoever, and it's going to work. So that's a really cool feature.
Cool. Yeah, I mean, I haven't actually, well, I've shared pictures before, but I don't normally pass models around. So I've never been really careful about, you know, what I'm doing on my own directory. So what that means is I suspect that I might sometimes use something and not actually realize that I've wired it into something that's only on the machine. If I go with the last method, at least anyways. What else can I say? The one thing I can say everybody seems to talk to is do evaluate that the model that you've got from a vendor, by the way, is actually working in the manner that you anticipated. Apparently people who are keeners, you know, they'll take the data sheet and they'll look for certain parameters and figure out how to look at it. That matters if you're a keener. I mean, for the stuff that I'm dealing with like transistors, I'm just, you know, I'm just basically dealing with the roll off problem. You know, it rolls off at wherever the Miller capacitance kicks in. You know, so that sort of stuff is pretty trivial, and I think you don't have to go too far to see that, which is why I used the diagrams I did.
Okay, Pete.
Okay, I like the idea that how you showed first with the copy. You know, go somewhere, copy the file, the appropriate parameters for the model, and then insert it into the library file. I like that method. It's I wouldn't be worried about it. I mean, I guess if you messed it all up, you could always reload Spice. But I think that's the easiest way. Dave is right. Although I was on the receiving end of the problem, and Dave just highlighted a problem that was huge in about 5 seconds. The file he sent me took me hours to find the model, and the person, Wayne, who you referred to, the Russian, I think eventually I did go to him find the model. So there is a place to put the model into your spreadsheet, or not spreadsheet, into the worksheet. I got Excel in my head. Into the well, whatever you call it in Spice, you know, right on the schematic. And then when you send that to another person, then he's got that model. It's okay if you've got the model that comes standard with Multi Spice, but if it doesn't.
Okay, so the everything that I used, I think, but the well, let's have a look at it here for a second here. I'm going to look at my own screen here. Not sure it just yet. The last method was making your own component that points to a library. That is not portable unless you mail the file that the library's in. Okay. Go backwards. I'm just playing on my machine here. Pardon me. The first method I showed was including the text of the model. Is that what you mean by include?
Well, the very first way of showing it, that's what I talked about. I thought was a good idea of doing.
Oh, sorry. Yeah, the first way of putting like a component model, it's always better to put in the drop-down list. I think it's just because it's easy to find those models. You just Google them and they come up. Right. So the third way, I was just using the text of the model right on the screen, but I had a couple of operational amplifiers. That is highly portable, but you run out of real estate pretty quick. Okay. And the fourth way was I had a library statement pointing to a single subcircuit. Okay. And the subcircuit, in my case, I put it into my LT Spice directory, so I didn't have to put a file in there. And then the fifth way, well, I just created a symbol from a library just to prove that you can do it, and it was automatically connected to the library that I was using. And my final way was, of course, what was it? I don't know. I can't remember.
just something just occurred to me, Wayne. When you got those large models like that 741 that's on your page, you know what, you could change the font on that one and go for a really small font because you don't need to read it.
That is completely true. You could do that.
Now I don't know how small you can go in Spice, but
yeah,
anyway.
you can certainly do that. And I'm sorry I didn't think about it. Font size is set to 1. So you know what? It doesn't look to me like I'm allowed to set it lower than 0.625.
Oh, okay. So you can't go that small. But anyway. Okay, that was it for me. Thank you, Wayne.
Okay.
Anybody?
Actually, I just thought of something here. What you could do, Wayne, you said that the .include includes all your commands, and you could have other Spice directories in there. So if you've got an include, and you've got your schematic file, and in the same directory, you've got the include file that has the model.
Right.
You could send both of those files, right? And then
Absolutely.
receiving it could put it in their directory, load it, and it's going to work.
The only thing I'll say about that is this is something I learned from the internet but never tested. So you want to just try it and see what happens, just once. If it's if it blows up, I'm just listening to the wrong internet guy. Okay, but the advice was, include files, do more. You can see this on the LT Spice help as well. It tries to explain it, but I'm interpreting that as it's executing your simulation commands for you, just as I said.
Okay. Anybody else? Comments, questions? No? Okay. Good stuff there, Wayne. Okay, up next is Kevin with a cool circuit or cool chip.
Yeah, or something like that. Okay. This is quick, 5 minutes as usual or less. All right. Let me do the screen sharing thing. Let's there we go. We want that. Does everybody see that?
Yes, sir.
Yep.
Okay. So we'll start from the beginning. Okay. So you can hear me, you can see it, we're good? All right. So this is a complete opposition to all the single transistor amplifiers and receivers and stuff that we've done in the past. And one nice thing about this group is that we do that level, but we also build blocks or takes blocks of smart stuff and make them into other things. So this one is a chip that does everything. It's like got worldwide FM band, AM band, shortwave, long wave, FM stereo, plus all the data that comes with the stereo signal, the song and name and all that kind of stuff. It's got digital tuning, digital volume control, frequency control, frequency synthesizer, and it's all with an I2C interface. And you're thinking, oh, okay. So the nice thing is that, and this is not a brand new chip. It's been around for a few years. It's just kind of new to me. So that's why I thought, okay, well, maybe some of you guys have heard of it, maybe not. So, that kind of lends itself to being controlled by an Arduino or something like that. And unfortunately for Dave and Peter, there's no crystal filters or mixers in here. But very few components, as you can see, a couple of antennas, FM, AM, some control signals, a power supply, and you got some audio out. Really simple. And so you might think, oh, it's a lot of programming, right? Well, some guys have done all the hard work for us. There's a GitHub repository. He's got a whole bunch of different receivers in there, all coded with schematics and everything else. He runs a Facebook group. He's got a complete library for interfacing to these chips. Another guy, and there's an example on there of a sideband receiver with an Arduino and a little OLED display. And you can use other 18 mega chips, including the ARM processors, ESP32s, all that kind of stuff, all programmed through the Arduino. And the sideband is not a native mode. I think you're supposed to pay for firmwares or something like this. But some guy, reverse engineered it, and there's a patch that's been published that you can store in the Arduino, and you load it in, and so you get sideband as well. And this thing's current. I did this on Sunday, I think, and so the latest update was like the day before. So this GitHub library. So anyway, there's a lot of stuff there. This is a schematic from GitHub with the OLED display. There's the chip here, a couple of antennas, crystal oscillator, audio output with some decoupling caps. Your Nano, no, it's a Pro Mini, sorry, and an OLED display. Then your control buttons and an encoder. That's it. There's another guy from this is one Peter sent me. Hackster.io did a complete AM/FM sideband receiver. As you can see, there's very little to it. Anyway, I thought that was pretty cool. The full featured version is $26 at DigiKey. So it's not cheap, but it's also not expensive. So anyway, I thought it was kind of neat, but maybe not.
Yeah, 25 bucks is not bad.
Not for a complete radio. If you figure the time you spend doing all the stuff that you want to do, it's and the library is already built for you, right? So you don't have to spend time developing software. But if you want to build a radio and just mess around as a second receiver or something, yeah. Anyway, I thought that was kind of neat. So
it's pretty cool.
Short and sweet. That's this month's.
What's the chip number? SI4735?
Yeah, the SI473, and then there's a bunch of different ones, depending on what features you want.
Okay.
But if you just search SI47, receiver, it'll come up.
Okay, cool. Wayne, go ahead.
Yes, I was just going to ask if the Arduino crew were dealing with something more sophisticated than a crystal oscillator, like a local oscillator plugged into it. That they have models for that.
As part of this chip?
No, I meant when you looked in the Arduino library section, or maybe the pictures I saw of people actually making these things. They're tunable, right?
Yeah, no, this thing has its own oscillator and everything on board. You don't have to do anything external. You just send it an I2C command to go to this frequency.
That's nice. Okay.
And then do you want FM? Do you want stereo? Do you want AM? And it takes care of everything. You don't have to do anything as far as tuning or controlling some kind of VFO.
Okay, Pete. Okay, go ahead, Pete.
Oh, okay. I saw a couple other hands up there as well, Drew and Dwayne. I was always thinking, that might should we classify that as homebrew?
Yeah, is it?
Someone said like next month we're going to be doing a little session with homebrew transmitters. But it occurred to me when you were going through your presentation there, Kevin, that let's classify this chip as a homebrew receiver, because some of it is about homebrew receivers is a selectivity or these kinds of things. I'm wondering how the performances of this particular chip. But $25. Got Christmas coming up in a year. So.
It's not from what I've read online. It's pretty good actually. I mean, they use it in clock radios and stuff like this that you buy for $20 at Walmart or whatever. That's the target market. So, but it can do shortwave, everything, all ham bands up to 30 megahertz. So, is it something you want to do for a fancy receiver? Maybe, maybe not. But from some of the reports I read, it's actually quite good, even in sideband mode.
Sounds like a chip waiting for somebody's bench here.
I'm getting one.
Looking forward to your report.
Won't be happening for a while.
Yeah, and for the Arduino stuff, I mean, I don't know if anybody's heard, but the Arduino 2.0 beta is out, And Dave, it's based on Eclipse. Full-blown debugging, proper code refactoring, all kinds of good stuff that comes with Eclipse. So I can't wait till they get it out of beta.
Have you seen Platform Mile?
No.
You got to check that out, man.
Yeah. Okay.
The cat's
that was just an aside. So
yeah, if you like Eclipse, look at Platform Mile.
Oh, okay.
Anyway, going off topic. I think Dwayne had his hand up.
Yeah, go ahead, Dwayne.
All right, there's a bunch of YouTube videos about different receivers on there. If you go to eBay, there's a kit with a 4732 all band receiver. You can get in kit form with programmed Arduino, the chip, PC board, all the other components for about $35.
Wow.
And several other ones. You can get a complete one, all assembled in a case, for about $55.
Okay. Yeah, that's, you know, if you don't have the bits laying around, be a nice little kit for some. You know what? It'd be a nice starter kit for somebody that isn't necessarily a ham yet.
Yeah. Okay. I'm not sure if it was Dave or Drew had their hand up.
Well, I had my hand up, and I was just looking for a link for that because I was just thinking what a great little chip to put together. And I just received 3 OLED displays. I have a few Arduinos sitting around not doing very much, and sounds like with a couple other parts, I could pretend to build myself a receiver.
Yeah, I think if you just search SI47 breakout boards, you can even get them off eBay for just a few bucks. I think they're cloned chips, but
that's perfect.
If you just want to mess around, then and you don't necessarily need the official chip, you know, that's a possibility too, from what I've heard anyway.
Well, if the code's already on GitHub, I've conquered that to a certain extent. So
yeah, no, it's there's full. You go in there, it's full blown libraries and it's up to date. They're keeping. It looks like there's a lot of commits and stuff that are current. So.
Oh, that's great.
Yeah, it might be a nice little receiver to take camping.
Yeah, or just mess around with and do whatever you want.
Rat 3.
Okay, I don't know if anybody else. Any more questions or comments? No? Good.
Okay.
That was cool, Kevin. You must spend long hours at night looking for these cool chips.
Actually, I just get a couple of email things, and oftentimes it shows up in like DigiKey or something, and that leads me down a rabbit hole. And I've got a list actually to go through, so it's not like I'm spending time looking for the stuff.
Cool.
So we're good that way.
Alrighty. Thanks, Kevin. That was neat. Okay, Peter, you got to talk about your voltmeter data logger.
Yeah, okay. It'll only be a couple of minutes with this, but just a real quick overview. I may do a little more in-depth presentation down the road, but for now, the genesis of this project started actually when I still was in Toronto many years ago, when I discovered the 8307 chip, and I started to analyze it to see what it could do and how it worked and whatnot. And I ended up with a couple of pages of data. You know, the usual frequency, DC voltage measure, jot down in a notepad, change the frequency, repeat another 100 times. And then you got to type it all into an Excel sheet. And I thought, well, there's got to be a better way than doing that. But life was too short at the time and had other projects, and we carried on. So since then, I've probably had about 5 or 6 more projects that entailed a couple of pages of data that had to be hand transcribed into Excel to analyze it. And this last month, I decided enough was enough, and I was going to do something about it. So the first design, well, I was also taking an interest in op amps at the same time. So my first kick of the can was I thought, let's do a 2-channel voltmeter with an Arduino. That should be really easy to do. No big deal. Maybe one day at most, and it'll be all done. That didn't turn out to happen at all. It took me, well, I'm still at it. But The idea there was to have one positive voltage channel and the other one was going to be a negative voltage channel because I was now interested in op amps. And of course, we had the plus and minus rails and I wanted to measure it. I did not want to reverse the leads. Why? Well, today I would reverse the leads, but a month ago I wasn't going to. So I started to do that. Long story short, I decided that wasn't really a worthwhile endeavor. I got it to work. It worked great, although it did cause me to blow up a few things, and I'll discuss that at a later date. And the amount of times that I would use it wasn't worth it. So I decided, well, let's go with a 2-channel, 2 inputs for DC voltages, and a 3rd channel. Let's do frequency, because like I say, back in the 8307 days, frequency, a power level, a DC voltage level, they're all important. The other thing I decided to do at the time was to export it into a spreadsheet automatically. I didn't want to have to handwrite anything. I didn't want to move a data card around. I just wanted Excel to accept it. So got that to work. It took me a little while to be able to control the data stream, but I managed to do that, and everything's working quite well. However, let me backtrack a little bit there. It didn't work exactly perfect. I couldn't control it quite exactly, but the biggest problem was I was using a nano at the time. And whenever I plugged the nano into the USB port, which of course you're going to need when you want to export the data into a spreadsheet, it changed the values on how the nano was recording or measuring the voltage. It dropped it down by, I think it's about a volt, or maybe not quite a volt. I can't remember. Anyway, I didn't really figure it out what was going on at the time. So to cut my losses there, I decided to go with, okay, let's use an SD card. So I put in a data shield, or a data logger shield with an SD card, and I started to go down that path. Now, that meant getting rid of the nano and switch to a Nuno. So I started to do that, and in the process of doing some coding for the data shield and all that, I realized that when I didn't have the same problem with the Uno as I was having with the Nano, and it was not altering the way the Arduino was measuring the voltage. So I thought, well, maybe I'll go back to the spreadsheet stuff again. So I abandoned the data shield, and by the way, I went and bought a data shield. And then after rummaging through some stuff and doing that, I discovered I had another data shield already in the box. I just didn't know I had it. So anyway, so now I got 2 data shields with nothing to do. So I got the spreadsheet to work fine with the Uno. Everything's fine. It exports great. It's formatted the way I want it. I can control it where you just push the button. Even if you hold the button down, it'll only give you 1 reading. So you could make your adjustments to whatever you want to adjust. Push the button, it'll take a data point, send that data point into a spreadsheet and populate your spreadsheet. Of course, you can build your spreadsheet with graphing, whatever you want, so it'll auto-populate. And so I thought, well, now I can start thinking about packaging it all up. And then I thought, well, why do that? Let's keep going, because I was going to delay the frequency reading capability. So the last day or two, I've been kind of noodling how I'm going to do that. And that, I think, is going to be a fairly good challenge for me. I haven't dealt with the chips that are involved in, dividing the frequency down and then Schmidt triggers and all these kinds of things. So anyway, it'll be a good learning curve, but that's where we're at with it now. So it works perfect for DC voltages and sending it into a spreadsheet, auto-populating. Now the challenge is frequency reading. So anyway, that's my project for the moment.
Very good, very good. Okay, anybody questions, comments? No? Okay. Well, I think that about wraps it up. Does anybody else have anything they want to quickly talk about? No, we're good. Alrighty, guys. I think it's time to call it a night. I need to get to bed.
Well, bed.
I know. It'll be the first time in 4 days for me. Okay, good.
All right, it was good seeing everybody out tonight.
Yeah. I think we hit one point. We hit 48, 12, 6. We hit 20 people tonight.
Oh,
so we're getting bigger, guys. And it was good to see everybody. So I must say adieu.
Thanks, guys.
Everybody.
Okay, thank you, everybody.
Yeah, see you later.
Good night,
Okay, have,
guys.
Good
have
night,
a
all.
good night. Night.
So Eric,
Hey there.
did you